Good, how are you?
Good. So you must have a test coming up or something, huh?
I have to retake a quiz, and I kind of screwed up on a couple of questions.
Okay. Should we
So,
begin on this page?
yeah,
Okay. Which one? Does the red mark indicate the ones you missed?
yeah.
Okay. Shall we begin? I can't see that one up there.
That one I understand why I missed.
Okay.
But,
Well, before we go on, that looks like the hardest one on the page. So let's just talk about that one for a minute. I can see enough of it that I can see everything I need to see.
yeah.
Okay, they're asking for the phase shift. And the function to say 2 pi over 5 x plus what? What's that number right there?
4 pi over 5.
Minus 3. What's the standard equation of a sinusoid function? What's the general format?
Isn't it just is it a cosine, or
A sine.
A sine, then parentheses bx minus c plus d?
Correct. And it's called a sinusoid function, even though cosine works just fine. You don't have to have sine there. Sine or cosine. Okay? And the reason I asked you for that was because there are other formats for that. There's another format where the b is outside the parentheses. Well, in this particular case, what is the phase shift equal to?
Was it negative b over c? Or is it flipped?
It's negative c over b.
Okay.
Okay. Because the other format would be a sine and the b is outside the parentheses. If I'm in this format, then the phase shift is c.
Okay.
Okay. But if I'm in this format, in order for me to get the b outside of the parentheses, I have to factor it out. And so if I start with the b inside the parentheses and I factor it out, I now have a b outside the parentheses, and this has to be c over b, right? To be the same thing. In other words, this is the same as that. So all I've done is factored a b out. Well, once you have the b outside the parentheses, what you have left is the phase shift. That is the phase shift. So in this case, the phase shift is going to be 4 pi over 5 divided by 2 pi over 5. What's that? 4 pi over 5 divided by 2 pi over 5, or multiplied by 5 over 2 pi. Same thing. 2.
So it'd just be 2.
2 to the right.
Okay. Yeah, I screwed up on that negative.
Well, you went 2 to the left, but your mistake was not, that's an easy mistake to make. You didn't make the big mistake, which is to assume that that is the phase shift, which it would be if the coefficient was 1 or outside the parentheses. So it's really, there's a reason why there's all these different formats in trig. there's a lot of times where this is the format you want it in, and there's lots of times where this is the format you want it in. Just so long as you know. All right. And whether it's cosine or sine does not affect the phase shift at all.
Yeah.
Is it odd?
Yeah.
Odd means it is reflected over the origin. Okay? If I take this part and I reflect, and reflecting over the origin is the same as reflecting over the y-axis and then reflecting over the x-axis. So when I reflect this thing over the origin, it looks exactly like that. And that's what makes it odd. Is it increasing?
Yeah.
Is it boundless?
No.
Is it bounded? Don't.
Yeah.
In other words, if you knew nothing else, you would know that the answer has to be either C or D, correct?
Yeah.
It cannot be both boundless and bounded. Is it continuous?
This is where I didn't get it, because
Continuous merely means I would have to lift up my pencil to draw it. I don't need to do that. I can draw that thing without lifting my pencil.
oh, okay. I thought continuous meant it stopped at some point.
No, continuous merely means, in other words, if I have a function like this, that's not continuous. I had to lift up my pencil to do that part right there.
Okay.
Okay? If there's a hole in it, it's not continuous, because I got to lift up my pencil to get by that hole. I cannot draw that function without lifting up my pencil.
Okay.
Okay, now, which brings us, we know boundless or bounded is the answer, but let's figure out which. Boundless means what?
It never stops.
Correct. What do these two dots mean?
Endpoints.
Yes. In other words, this function is completely different than if I had arrows on it. If I had an arrow right there, then it would be boundless in both directions. It means it would be bounded by infinity on top and bottom, which makes it boundless. But if it is, this one is bounded by pi over 2 on top and minus pi over 2 on bottom.
Okay.
Notice that this is the inverse of sine, as drawn from -1 to +1. Okay, so question 6, what are the domain and range of arc cosine? Let's talk about that for a second. If I draw the sine curve, and I want to talk about the inverse of that, I have to restrict it. I've got to restrict the domain from minus pi over 2 to plus pi over 2. The range goes from +1 to -1, right?
Yeah.
And when I reflect this over the line y = x, which is how we get all inverses, my domain and range change. And in fact, if you look at this drawing, this one right here, not the one on number 6, but this one right here, that's exactly what they have done. They have taken the curve from minus pi over 2 to plus pi over 2. They've reflected it. And what we're looking at here is the arc sign or inverse sign. Okay? And notice what happens to the domain and range. Before, the domain was minus pi over 2 to pi over 2. The range was minus 1 to plus 1. Well, when you take the inverse of any function, the domain and range switches. Becomes exactly the opposite. In other words, whatever was the domain now becomes the range. Whatever was the range now becomes the domain. Well, let's look at cosine. Cosine, ooh, the heck, how did I get that? Wow, now I can't get it back? Are you kidding me? Oh, it's because I was pushed the wrong thing. Okay. If we look at cosine, cosine goes like this. Notice that in order to do the inverse cosine, we have to restrict the range from 0 to pi. First and second quadrant. Not minus pi over 2. In other words, if I want to come up with the inverse cosine, I start with this. Notice that that is 1 to 1, passes the vertical line test, passes the horizontal line test. That means when I take the inverse of this function, it is going to be a function. What's the domain of this function? 0 to pi. What's the range of this function? Minus 1 to 1. So when I take its inverse, these are going to switch. So the domain becomes minus 1 to 1. The range becomes 0 to pi. So there's the answer we're looking for. Minus 1 to 1 for the domain, which is answer B, C, and E. And 0 to pi, right there. B is the answer.
Okay, so I just didn't flip on that.
There's a lot to that question. There really is. Probably the most important thing to know is that when you take the inverse of a function, the domain and range flip, switch. Whatever was the domain is now the range. Whatever was the range is now the domain. Now, this is a bit, in other words, mathematicians came up with this domain restriction. They restrict cosine from 0 to pi for a reason. If they restricted it from minus pi over 2 to pi over 2, then its inverse wouldn't be a function. Would not have 1 to 1. So I have to know how mathematicians have restricted cosine such that inverse cosine is a function. And with cosine, they restrict it from 0 to pi. With sine, they restrict it from minus pi over 2 to plus pi over 2, because that is where it's 1 to 1. Okay, in other words, the domain on the sine is different than the domain on the cosine for purposes of talking about its inverse. I mean, if I look at the entire sine curve, then domain is all real numbers, right?
Yeah.
But if I were to flip this over the y equal x axis, it wouldn't be a function. So mathematicians arbitrarily decided They could have picked any 2 points. They could have picked from there to there. It's 1 to 1 in that interval. So they picked minus pi over 2 to pi over 2 for sine and tangent. But for cosine, that wouldn't work. For cosine, they picked 0 to pi because that is 1 to 1 and that inverse exists.
Okay.
So it's really kind of tradition. In other words, it didn't have to necessarily be that. It's just mathematicians at one point decided to make these restrictions, and it was somewhat arbitrary. They could have picked 0 to pi. They could have picked pi to 2 pi. But they did pick 0 to pi, and you need to know that. Number 8.
Yeah, I don't really understand how to write these graphs as it is, so trying to find it.
Okay, these are a little tricky. First of all, what is that function? What is it typically called?
So, absolute value, it's
the greatest integer function.
okay.
In other words, if I said graph this, y equals greatest integer function, and I put it in a bracket like that, it means if x is 5.6, then the greatest integer is 5. If x is 5.9, the greatest integer is 5. If x is 5, the greatest integer is 5. If x is 4.999, the greatest integer is 4. Okay? So, if I were to graph the greatest integer function, when x is from 0 to 1, the greatest integer is 0 until I get to 1. Oops, that's open dot. And then when x is from 1 to 2, the greatest integer is 1. You with me?
Yeah.
And it's always closed dot on the left. The next level, one way to think about this would be the age of people that are in first grade. If you are from 6 years old to 7 years old, you are in first grade. If you're 7 to 8, you're in second grade. It's the closest example I can think of that is a real-life function that is the greatest integer function. So, all we have to do is we know we're looking at some translation of the greatest integer function. The question is what is it? How does this graph compare to this one? Well, first of all, my open dots are on the correct side. They're on the right side of each one, right?
Yeah.
Okay. So these numbers in here, if they've got a combination of them, and combinations, in other words, this could be anything. This could be +1, right?
Yeah.
Wouldn't that be the same thing? If I took the function that I've drawn on my drawing tablet and I shifted it up 1, it would be what we're looking at. Correct? And the greatest integer function goes that way too.
Yeah.
Okay, in other words, it goes to the right and the left. So this would be one answer, but that answer isn't on there. The other way I could get this function is to start with this function and shift it left by 1, correct? In other words, another answer would be this. A left shift means that. Okay, you with me?
Yeah.
Okay. In other words, both of these y's would give you the function we're looking at. So what happens if I shift left? I've got to end up with a +1 here. Which of these answers gives me what looks like it's going to be a +1?
D.
Okay, let's test D. And like I said, these are a little tough, but first of all, what would this part of D look like? That would mean I would take the function below here, and I would move everything 2 units to the right, correct?
Yeah.
So this one would be starting at 3, or excuse me, starting at 2, and it would go like this. Well, how do I get from that to this over here? I got to move it up what?
3.
That gives me that. So if I take that and combine it with a vertical shift of up 3, get what I'm looking at. Now, it's a little difficult to go in the opposite direction, and you can see why. In other words, there was not one unique answer. There were at least 3 answers. I came up with 2 other answers, but the advantage of coming up with the other answers is it kind of gave us a clue that this plus that have to be +1. And the only answer on here that gives you a +1 is D. And then if we examine D and we see what, how you would shift that function over 2 units to the right, up 3 units vertically, you get this. Now, they could make it a little harder if they shifted and put the open dot on the left and the closed dot on the right. That means there's a negative involved somewhere. It means it's been reflected over the y-axis, if that's the case. But that was not the case here. This was a relatively simple one.
And this, I just need help kind of like memorizing what the graphs look like.
All right. I'll go through these really fast. Maybe it'll help. This is hyperbola, y = 1 over x. This is y = sine x.
Yeah.
This is y = square root of x. This is y = e to the x. This is y = absolute value of x. This is y = natural log of x because it is the inverse of y = e to the x. This is y = x cubed, and this is y = cosine x. I don't see,
Okay.
I don't see that last one on there. You see cosine anywhere? No, they put 8 graphs and only 6 answers.
Yeah, they were trying to confuse us.
Okay.
Because the square one, squared isn't up there either.
Well, the square root of x is there, and that's c.
Oh, no, the absolute value isn't up
Oh,
there.
the absolute value one is the other one that's missing. Yeah, this one and this one are not up here. Now, let's talk about how to memorize. First of all absolute values look like this. There's a big giant V. Also, all absolute, I can't say all absolute values are positive, because if I said y equals minus absolute value of x, it would be this curve reflected over the x-axis. You with me?
Yeah.
Okay. This is hyperbolic in nature. There's a ton of functions that are hyperbolic, and they all end up with some form of x in the denominator. Another example of a hyperbolic function would be this. Y equal x plus 1 over x minus 1. That's going to graph something like that, okay, with different asymptotes. It's the only difference. But the most basic hyperbolic function there is y equal 1 over x, and that's that right there, A.
Okay.
The sine curve. By the end of trig, you should have the sine and the cosine curves memorized.
Yeah, I do.
Okay, you got the sine one correct, and the cosine one wasn't on there, so I don't see any h's up there. Good. The biggest way to memorize them is that sine of 0 starts at 0, whereas cosine of 0 starts at 1. There's only one function that looks like this. Notice what's unique about this function. Its domain is all positives, no negatives, and its range is all positive, no negatives. That's this function right here. X has to be positive or 0, and y has to be positive or 0. And there's not very many functions that look like that. Okay? This is clearly exponential in nature. It doesn't have to be e to the x, but that's the only exponential function that's on there. Exponential meaning the variable is in the exponent. There's a big difference between 9 and 12. 9 is not an exponential expression. The variable is on the algebra line. 12, the variable is in the exponent. Now, pretty much all exponential functions have this shape. If you just gave me that function and said, what is it? Well, that could be 2 to the x, it could be 5 to the x, it could be e to the x, it could be most any of them. I can't tell by looking at this function. They all go through this point, 0, 1. Okay? Now, natural log of x is the inverse of e to the x.
Okay.
And if I take the inverse of that, I get this down here. Notice that all natural log functions, or for that matter, log of any base functions, go through this point, 1, 0. And this goes all the way down to negative infinity and goes to positive infinity on the upside.
Okay.
Okay, but the domain on this one, the natural log function, has to be greater than 0. Cannot even be 0. This, on number f, that y-axis is a vertical asymptote. The natural log function never touches the y-axis. Why is that? Because you cannot take the log of 0. It does not exist. It's imaginary. But you can take the log of any positive number. And finally, this, you should memorize that as x cubed. In the same way that you know what x squared is. In other words, if I said, what is y equal x squared, what does that look like?
Isn't it just, parabola?
Parabola. All quadratics are parabolas. Okay, well, y equal x cubed does that. And notice that this is also odd. In other words, this is symmetrical about the origin. And another good way to memorize which functions are odd and which functions are even is by using these two functions. This is even because the exponent is even, and if I plot that, I get something that is symmetrical over the y-axis. All even functions are symmetrical over the y-axis. All odd functions are symmetrical over the origin.
Okay.
So if I look at the sine function, is that even or odd?
That's odd.
If I look at the cosine function, is that even or odd?
That's even.
Correct. And it's hard to memorize with cosine and sine unless you know the exact appearance of the function. But it's easy to memorize with parabolas and cubics because this is an odd number, that's an even number. All right.
And that's it for the quiz. Can we do ACT stuff?
For the next hour? Sure.
Yeah.
Okay.
Because my mom wants me to start like fully studying for this.
Yeah, and in fact, I have as soon as we get done with the McGraw-Hill here, and we're almost done with that, I have a special practice test. Let me open it to you and show it to you. We don't need to do this one tonight, but we want to start working on this one. And the difference is, this isn't the one I was thinking. I had a teacher parent cut out a bunch of geometry problems and paste them together. And I've got that somewhere. I'll have to find it. A second, let's see if this one's it. No, maybe. Hold on. No. I've got one that's almost exclusively geometry problems, which is a really good thing for you to work on. Not because you're weak in it, but because it's been 2 years since you took geometry. And most people who take the ACT test, especially students who are a little ahead of the curve, end up weak on geometry. So it's definitely going to be worth our while to practice those geometry problems. I just got to find them. We'll pick up where we left off, 455. Now, 45 is where we left off. You remember it? How many ways can you arrange? How many three-letter orderings can you make with the letter ponies? Now, it's probably worth going through this one time. You are only going to get at most one question on the ACT test regarding this kind of problem.
Okay, because they take forever.
No, it's just you have to understand one thing. You have to understand what NPR is, like National Public Radio, and you have to understand what NCR is. You have to know the formulas for them. This formula is n factorial divided by what? R factorial.
No.
This formula is n factorial divided by n minus r factorial times r factorial. Notice in the bottom one there are two n's and two r's. In the top one there's only one n and one r. Now, first of all, there's two things. How to do these and how to decide whether we're going to use the pick or the choose. This is a permutation. This is a combination. Permutation order matters. Combinations order does not matter. For example, 3 letters that I can pick are PON, right? There's one 3-letter ordering. Well, another one would be OPN. If order matters, this is 2 different ones. If order does not matter, it's the same one.
Okay.
You know the rules of poker?
Yeah, kind of.
You know what a flush is?
Yeah.
Flush is 5 cards of the same suit.
Yeah.
Okay? But the order doesn't matter. In other words, if I have 5 hearts in my hand, it doesn't matter whether, even if I have the ace of hearts, I don't have to have the ace of hearts as the first heart. I can have it as the 3rd heart. So in poker, these 2 things are the same thing. If I have PONI, I have a flush because I have those 5 letters. If I have OPNEI, I still have the same exact flush. Order does not matter.
Okay.
Okay, so when order matters, I use this one. When order doesn't matter, I use this one. Well, order matters here. PON is different than NOP. So I'm going to use the permutation formula. Okay, and it's as straightforward as it looks. There's 6 letters, so I have 6 that I'm choosing or picking 3 from. So 6 factorial divided by 3 factorial. Now, let's talk about how to solve that. You might be able to use, I don't know, don't they give you a special calculator when you take your ACT, or do they let you use your standard calculator?
They put us in press the test mode.
Okay, so I'm not sure you're going to have factorial on there. Do you know how to solve that I've written right there manually? First of all, what's 6 factorial mean?
Oh, it's 6 times, it's 6, then everything under it.
It's 3 factorial.
3, 2, 1.
What's the result of those? What's the result of that math? Since I can cancel all of those.
$120.
There's 120 ways that you can arrange 3 letters from the 6 given.
Okay.
Okay? And this factorial thing, you get kind of used to it after a while. In other words, if I had 7 factorial over 5 factorial, I know that's 7 times 6. Because everything from the 5 down will be canceled out by the bottom.
Okay.
Okay? Now, if the question, let's just talk about this because they said order doesn't matter, so, or we were able to figure out rather that order matters. Well, if I was talking about a problem where order didn't matter, then I would use the choose one, and I would have 6 factorial in the numerator. In the denominator, n minus 3 is a 3 factorial, and there's 2 3 factorials in the denominator. So now what I end up with is 6 times 5 times 4 over, in other words, that takes care of one of them, over 3 times 2 times 1. So now I've got 120 divided by 6. There are only 20 ways to arrange 3 letters out of those 6 if order doesn't matter. In other words, if you were trying to figure out how many ways can you get dealt a flush out of 52 cards, you're going to use that because your flush order doesn't matter.
Okay.
Okay? So you can kind of see why I didn't want to spend a whole lot of time on this. It can be kind of complicated. And you're only going to get one problem. And I'm going to be straightforward with you. These are hard because it's hard to figure out whether order matters or not.
Okay.
If I told you I have 5 ladies and I have 5 chairs, how many different ways can I sit those 5 ladies in those 5 chairs? Does order matter or not?
No.
No, it does. Here's my situation. I have 5 chairs. I've got 5 ladies. I'll call them A, B, C, D, E, F. Okay? Well, if A is sitting there, C is sitting there, B is sitting there, D is sitting there, F is sitting there, that's a different arrangement than if I sit C there and A there. This, and B, D, F. So order matters very much. In other words, if you looked at the 5 women sitting in this arrangement, it does not look the same to you as the 5 women sitting here. In this case, Lady A is sitting in seat 1. In this case, Lady C is sitting in seat 1. So it's not a terribly easy thing to figure out where order matters and where it doesn't. But in the problem I just gave you, which you might find on the ACT test, the way to do that is not really with permutations or combinations. How many women can sit here? How many choices do I have of the 5 ladies to sit in this seat?
5.
After that lady is sitting in that seat, how many choices do I have for the second?
4.
The product of those 5 numbers is your answer.
Okay.
Okay? So that's not really a permutation or a combination problem, but order does matter.
Okay.
And that's the easiest way to figure out that problem. All right. Each side is 5 centimeters of a cube. What's the volume of the cube?
Isn't it just 5 cubed?
Yeah, I can't even read the exponents on any of these, but yeah, it's 5 times 5 times 5. In other words, it's the width times the depth times the height. All 3 dimensions. And that's whether it's a cube or a rectangular brick. If I've got a rectangular solid that has dimensions 5, 6, and 7, then the volume is 5 times 6 times 7.
Okay.
Okay. Yeah, hold on a second. Here's our function. That's the question. For what values of x is that expression positive? Two ways to do this problem. What are they?
Couldn't you move 15 over and then
No,
factor our x?
no, that's not one of them. One of the ways to do this problem is to back solve it.
Okay.
Okay. Let's do the easiest one first. That doesn't look particularly easy because it's got a negative 5/3 involved. But this one here, would this work? Well, let's see. If x is minus 6, what do we get? We get 3 times 36 plus 4 times minus 6 minus 15. Is that positive? 108 minus 24 minus 15. Yes, it is. But I think if x is 4, it's also positive, right?
Yeah.
Or minus 4, rather. Let's see. If x were which is not in that range. In other words, I might be able to rule this out as an answer by testing minus 4. Well, minus 4 becomes, this is still going to be positive, is it not? And now we have 48 minus 16 minus 15. That's still greater than 0. So B is not an answer.
Okay.
Okay. Back solving is going to be a little tough because B actually looks like it is an answer when we go to back solve it. As long as I let x be less than minus 5 or greater than 3, that is greater than 0. But it's not the correct answer. Let me give you one other way to solve it. Boy, these two problems here are toughies. I'll bet you have learned how to do this. You probably just forgot. First of all, you got to factor it. How does this factor? Given our answers, they got some 5/3 in there. They got a lot of 3s. They got 5s. They got 5/3. What do you think one of the factors has to be?
A 5.
Right. Well, they got some 5/3, so let's put the minus 5 over there. We know the signs have to be opposite. We'll put the 3 there. Does that give us a correct middle term?
No.
We get our middle term by checking the inside and the outside. That's minus 5x. That's plus 9x. Add them together.
Oh, yeah, it is.
It is correct. Okay. So, first step is to factor. Now, if that was equal to 0, it'd be a piece of cake. But it's greater than 0. When you're solving these kind of problems, you need to use a line chart. What are my critical points?
Is it negative 5/3?
Positive 5/3. The critical points are whatever makes that 0 or that 0.
Oh, okay.
So positive 5/3 makes this thing 0. Negative 3 makes that thing 0. Our next step is to plot those 2 points on my line chart. There's negative 3. There's positive 5/3. I purposefully leave off 0. The way I'm going to solve this problem is I'm going to look to the left, I'm going to look in between, and I'm going to look to the right. Pick any number you want. Now let's pick minus 4. Okay? When I pick minus 4, I get a negative there, and I don't care what negative, I just need to know if it's negative or positive. And I get a negative there. And then when I multiply a negative times a negative, I get a positive. What this line chart tells me is that everything to the left of minus 3 is positive. Okay? Now let's check a point in between. 0 is a great point. Okay? When I plug in 0 for x, that's negative. This is positive. Negative times positive is a negative. So all these values are negative in between. And when I check a point to the right of 5/3, let's say 2, that's positive, that's positive. Positive times positive is positive. So now if I want my answer, I need to know, where am I greater than 0? Well, it's in that range and that range. What does that look like? That looks like x is less than -3, or x is greater than 5/3.
Okay.
That's an obscure thing in pre-calc. Have you done line charts?
No.
Because these aren't that hard, but if you have a quotient, let's say I told you x plus 2 over x minus 3 is less than 0. Well, you got to use a line chart to solve that. There's no algebraic way to do it. You have to use a line chart, okay? The first step is to figure out your critical points. Well, in this case up here, the critical points, what makes the denominator 0, what makes the numerator 0? So my critical points would be -2 and 3. So when you start out with a quadratic like they gave us, then your first step has to be to factor it. Once you get it into this step, then it becomes relatively simple to solve using a line chart. But you have to use a line chart. Okay?
Right.
And I would say that as long as you know how to use a line chart, this is the easier method than back solving. In other words, this was not easy to back solve. Like I said, we weren't really able to test all 5 answers and see if all 5 answers could potentially be correct. In other words, B is true, it's just not the correct answer. They want all values of x that make that positive. Well, B is just some values of x. So it's a tough one to back solve. So I'm not sure. It might take me 10 minutes to back solve this thing before I came up with the correct answer. Whereas I can factor that in about 20 seconds, and then I can use a line chart. It takes about 30 seconds. So it's not a hard problem if you use a line chart. Once again, you're not going to have any more than one of these. In other words, we're in the high 40s. That's where the tough problems start. Although you can certainly see that 45 was tough, 47 was tough, 46 was a piece of cake. 46 was a beginning problem. But 45 and 47 were definitely toughies. And I always question how much time I should spend with students on the super tough problems. That's not where you're going to score. You're going to get your good score by getting all of the easy ones, all of the mediums, and some of the hard ones. If you're going to miss 10 questions out of 60, you're going to get a pretty good score. You want to make sure those 10 questions are all the hard ones, okay? In other words, spend your time on and I would tell this to anybody, no matter how smart they were. Spend your time getting the easy and the medium problems and put the hard ones off until you've done all the medium and the easy. And then if you still have time on the test, then you can do the hard ones. But prioritize your time. Which of these is a perfect square trinomial? And what that means is that when I factor this, I get a linear term squared, something like x minus 3 quantity squared. That would make it a perfect square trinomial. Or x minus 2 squared. Or, well, what's the trinomial if it's k?
Is it 2x plus 4?
Now, remember that this term has to multiply by itself to give you that term.
Oh.
Okay. But 2x plus 2 might be the answer. Let's expand it. What do we get? We get 4x squared plus 8x plus 4.
Oh.
That's not it.
Okay.
And it has to either be f or g. It cannot be h. Notice there's no way to split 2x squared up into the same term right there. You would have to have 2x times x. That's not a perfect square trinomial. So it's either f or g. If it were f, what would it be?
It would be 2x plus 3.
Let's see if that works. 4x squared plus 12x plus 9. We got it.
Okay.
Now, they didn't ask you to figure out that, but you kind of have to do that to solve this problem. You can't tell which of these is a perfect square unless you figure out what this is and then test it. I mean, I guess you could factor that. Go ahead and factor it, and you'll find out that it's 2x plus 3 times 2x plus 3. There's your answer immediately. So the answer really lies in factoring that.
Okay.
These are some good questions. We can stop. It's 5 o'clock. This looks like a good one to start with next time.
All right.
Okay. So when are you taking the ACT?
In April.
So do we want to schedule hour-long sessions every Wednesday until then?
Yeah.
I'll do it from 4 to 5
Okay.
every Wednesday. Does that work?
Yeah.
All right, Mitch. Have a good week. I'll talk to you next week.
All right.
Bye-bye.